Okay, so the last thing we were doing is we were talking about a seesaw, and we were saying we have certain masses and we can put these different masses along this seesaw here. And what we want to do is we want to find the center of mass. Okay, in the center of mass, I am going to call X bar. All right, so its location is going to be X bar. So let me erase this just a minute and put it right here. So that's the center of mass. Okay, so what we have is torque of a mass mk about the center of mass. We can calculate that torque. Okay, so the torque about X bar, which is going to be the center of mass, is to take the distance that the mass is from X bar, multiplied by its mass, and then of course use the gravity, because that's the gravitational force. That's the downward force. Okay, so what we get is this is a signed difference. I say signed difference because it depends on which side of the mass it's on. If it's on the right side of the X bar, all right, if it's on the right side of X bar, then it'll be positive. If it's on the left side of X bar, then it will be negative. This is the downward force. Okay, so that's the downward force due to gravity. Okay, so we want to balance the system. All right, so for a balanced system, the sum of the torques is 0. That means nothing is desiring to rotate. Okay, so for a balanced system, the sum of torques is 0. Okay, so then let's compute that. All right, so we're going to, so we know right here what we get, what I have here. This happens to be the torque of one mass mk about X bar. All right, so now we're going to sum them up. So that means we're going to have the sum k equal 1 to n, however many that we have. And we're going to take xk, we're going to subtract X bar times mk times g and set that equal to 0, because that's summing them all up. Okay, now the first thing we can do is take g out. Okay, so g can come out as the sum k equals 1 to n of xk minus X bar times mk is equal to 0. So now I can divide both sides by g, and the g is gone. Okay, so now I'm going to do the distributive property. K is equal to 1 to n. So I'm going to get xk times mk minus X bar times mk is equal to 0, because all of that is inside the sum. So now I'm going to distribute again, because if I can sum, the sum of this difference is the same as the difference of the sum. So I get the sum k equals 1 to n of xk times mk minus, and this term I'm going to factor out X bar, because X bar is a number, doesn't have a k in it. Sum k equals 1 to n of mk, and that equals 0. All right, so now I'm going to put this on the other side. So I'm going to get the sum k equals n, 1 to n of xk mk is going to equal X bar times the sum k equals 1 to n of mk. And then I can divide by s, the sum of mk, and I now have my final formula, which is xk, I'm sorry, x bar is equal to the sum k equals 1 to n of xk over mk times mk, and that whole thing is divided by the sum k equals 1 to n of just mk. All right, so now you can see that the denominator is just the system mass. It's the sum of the masses. So this is just the system mass. And the top, well, that is simply just the system moment. So there we go. The center of mass is just sum up xk mk and then divide by mk. So a quick example. Let's suppose we have something like this. Here is 0. I have a mass M1, which is 150 kilograms, and it is located at -3. I have a mass, so this is M1. I have a mass M2. It's located at x equals 2, and it is 50 kilograms. And then I have a mass M3, and it is located at 3, and it is 35 kilograms. Okay, so therefore, to find the center of mass, I need to first sum up the masses. So I get the sum, k equals 1 to 3 of mk is equal to 150. Let's see, what in the world is that? What is that? I don't know what that is. Oh, all right, that can go. I don't know what it is. Cut. Okay, so I'm going to get 150 plus 50, this is easy, plus 35 equals 235. So I get 235 kilograms. Okay, so then I need to find the system moment. So I need to take the sum, k equals 1 to 3 of each mass times its distance from the origin. So the first mass is 150. And it is -3, times -3. -3. My daughter always says, why do you say -3? I know it's -3 plus 50 times, and how far is it? I forget. Oh, it's at unit 2 plus 35, and it's at location 3, so I get -245. Okay, so therefore X bar, which is going to be then -245 divided by 235. Well, that looks pretty close to 1. So I'm going to get -245 divided by 235, and that's very close to 1. So I would expect that very close to -1, right about here. Okay, so this would be -1, -2, and then 1, 2, maybe 3 is a little off. 3 should have been a little closer. That should have been a little bit closer, like here. Okay, so notice the center of mass is very close to -1 because that one mass is much heavier than the others, and so it moves it across the line. Okay, so now we want to talk about the mass of a thin wire. All right, so let's think of a hair. Okay, so some people have perfect hair. Others do not. Some people's hair gets thinner at the ends. So we can talk about the density of it. So we want to, the goal is to find the center of mass of a rod or a thin wire. So here's how we derive it. Very simple. I'm going to create, for me, a very thin wire. So I'm going to assume that this is extremely thin. Doesn't look thin, but I'm assuming it. Okay, so this is my derivation right here. Okay, so here's location A and here's location B. And then if I just choose one small spot of this and I call this X, this is one little piece, delta XK. It's one little piece of thin wire, okay? And I'm going to locate it specifically at the point XK. So at the point XK, there's a interval called delta XK that's around it. Okay, so now I want to attach a mass. So we're going to attach a mass. At the point XK. So this mass, which is going to be delta MK, is a little piece of mass, and this is going to be at XK. So now that I have a little piece of mass, all right, I can talk about, let's try to figure out this problem again. So we have X bar. We already know that that's the system moment. Over the system mass. Okay, and the system moment, we already know the system moment well, that's the sum k equals 1 to n of xk. And now we're going to use delta mk, because that's the little bit of mass attached to that point. All right, so now we're in one dimension. So density generally is mass per unit volume. So in 3D, density, which I'm going to call delta, is mass per unit volume. In 2D, density is mass per unit area, but we're in 1D. Our density is going to be mass per unit length. Okay. All right, so now we can figure that out. So now I'm going to create something called delta at xk. So that's the density at xk is simply going to be a mass at xk divided by the length, which was delta xk. So that now helps me see that I can define my density in terms of my mass, or my mass delta mk is going to equal the density at xk times delta xk. All righty, so now I'm going to stick that into my sum. So therefore, those 3 dots, I hope you remember, they mean therefore, x bar, which we originally had was the sum k equal 1 to n of delta of xk delta mk divided by the sum k equal 1 to n of delta mk. We're now going to write this thing. We're going to put this in for delta mk. So therefore, we're going to get the sum k equals 1 to n of xk times delta of xk times delta xk. All right, yeah, that's right. That's what I want. Divided by the sum k equals 1 to n. In place of delta delta mk, we're going to be delta of xk delta xk. Okay, one is delta for density, and the other one is delta for a change in the x. All right, so we're going to take the limit as delta xk goes to 0, and that's the same as n goes to infinity. And these sums become integrals. So my new notation, and let me see if I have this already. Yep, there it is. So my new notation for x bar is going to be the integral from a to b of x times the density dx divided by the integral from a to b of delta, or the density dx. And this is very easy to compute. All right, so here you just have to note that my delta mk equal my density at xk times the length delta xk. And so that, when you do a limit, gives you a differential dm. So this becomes delta at x dx. So another way of writing this is to use the dm notation. And that is x bar is equal to the integral of x dm, where dm is delta, or the density of x dx. And then dm is just that part here. All right, so now we have a bunch of definitions. Yes.
Millions of players have discovered the world with Bingo Blitz. Download now and enjoy the ride. It's free. I'm all about that game, about that game.
Y'all are kidding, right? Okay. All right, so these are some definitions. I'll give you a minute to copy them down while I'll take roll. Okay. Okay, so these formulas are just the formulas that we just derived. The moment about the origin is going to be called m naught. It's the integral from a to b of x times the density times dx. The mass is just m. It's the integral from a to b of delta, the density dx. And the center of mass takes m naught and divides it by m. Okay, any questions about that? All right, so our first example. I like this example. It gives you everything that you need and it's not difficult. Okay, so here in this example, it says you are given a thin rod that is 10 meters long. So it goes from 0 to 10. So I already know my limits of integration. All right, which thickens from left to right. And here's my density function. So my density is 1 plus x over 10. Find its center of mass. Okay, so we can find m naught first if you'd like. So m naught is going to be the integral from 0 to 10 of x times 1 plus x over 10 dx. All right, so I have x just like up in here. I have my density function right here. And dx. Okay. So I now need to do this integral. This integral is the integral from 0 to 10. Inside, I'm going to get x plus x squared over 10. And then that's dx. So now we have to integrate this. And when you integrate this, you get 250 over 3. And this is, the mass was in kilograms. And then the density was in, why do I have kilogram meter? Okay. All right, so then we have to find the mass. That's the integral from 0 to 10. This time it's only the density. Remember, it is delta of x dx. So it's the integral from 0 to 10. Delta is just 1 plus x over 10 dx. And this number comes out to be 15 kilograms. So therefore, x bar turns out to be the m naught over m. M naught is 250 over 3 kilogram meters. And m is 15 kilograms. And so this turns out to be 50 over 9 meters, which is approximately 5.56. So somewhere down the line of this rod, approximately it is center of mass, taking into account how its thickness grows, is close to the center, but not exactly at the center. Okay, any questions about that? That was straightforward plug-in. Find what you need. Okay. After that, we have the mass of a plane region. All right, so now we want to take the mass of something that's laying inside of a two-dimensional region. So here's my, let's get rid of that and let's use just the other one. Goodbye, D. Okay. Okay. So here's my plane region. All right. And I want to find X bar. So here's my goal is to find where X bars should be located. Okay, I have no idea where X bars should be located. None. But I have different masses around. I don't want that red. I had different masses around inside of here, MK, and I can sum them all up. So now my goal is to find the center of mass. So you can find not only the X location, but the Y location. So this center of mass now is a two-dimensional spot because you need to find where X and what Y, where on this plane I can hold it and it will stay flat without flopping. Okay, so our system mass again is simply summing up the masses. Okay, so that's easy. But now I'm going to have two things. I'm now going to have a moment about the x-axis. And the moment about the x-axis, we're going to call it mx. And it is based on the desire of a mass to rotate around the x-axis. So if this mass wants to rotate around the x-axis, what's important to me is its distance from the x-axis, and that value is y. Okay, so therefore this is the sum, k equals 1 to n, and we're worried about xk times its mass, its displacement. That should be mk, that's why I'm confused. This should be a mass up, somebody's in the chat. Okay, so this should be each mass. But if you remember, we're looking at the distance that the mass is from where it wants to rotate. So when we had it on the seesaw, we took the distance it was from the fulcrum, that determined whether it wanted to rotate. Well, this thing wants to rotate about the x-axis. So I need its distance from the x-axis, and that is yk. Okay. And then the moment about the y-axis, so that's my. And that means this thing now wants to rotate about the y-axis. So it wants to go like that. All right, so if the point wants to rotate about the y-axis, we are concerned about how far it is from the y-axis, and that distance from here to there is xk, and then this was yk. Okay. So this is then the sum, k equals 1 to n of mk times xk. All righty. So therefore, the centroid, or the center of mass, well, we have to find the x coordinate. So the x coordinate is going to say take the x moment. So it's going to say take the x moment and divide by the mass. And the y coordinate is going to say take the y moment and divide by the mass. And that is exactly backwards. As soon as it came out my mouth, it sounded wrong. Okay. Okay, so here's all the equations. All right, so these are our definitions. The system mass is to sum up all the masses. The moment about the x-axis is to sum, mx is to sum up m, the mass, and the y, because that's the distance from the x-axis. The moment about the y-axis is to sum up the masses and the xk's, because those are the distance from the y-axis. And then the x coordinate of the center of mass is my over m, and the y coordinate is mx over m. Okay, so let's do one. Do I have one already set? Oh, I sure do. Okay, here's the example. So we want to consider a plane region with the following masses. So it has a mass of 4 at the point 2, 2. So let me see if I can draw this. Normally you don't have to draw it, but I just like to draw it for you. Just because I can. I need this much. No, I don't need. Okay, so I have a mass equal to 4 at the point minus -2, 2. So let me grab this again and move it down so it is exactly on the line. Okay, so at -2, 1, 2, 2, there's a mass that's equal to 4 kilograms. At 1, 3, there is a mass that's equal to 3 kilograms. At 7, 4, wow, 1, 2, 3, 4, 5, 6, 7. At 7, 4, there is a mass that is equal to, 7, -4, I apologize. Didn't pay attention. 1, 2, 3, 4, I knew something was wrong. At 7, -4, there's a mass of 11, and at the point -3, -2, we have a mass. So this one is M1. We had 1, 3 was M2. We had this was M3. And then this one is M4. Now, obviously, the center of mass is not going to be at the origin because this guy over here is going to throw us off. Okay, so the center of mass is not going to be at the origin. Okay, so now what do we do? To find the total mass, that's easy. All right, so the total mass, capital M, it's going to sum all the masses. So our masses are 4 plus 3 plus 11 plus 1. So our total masses are 19. Okay, so that's our M. All right. Okay. Now we need to find M at MX. Okay, so to find MX, we have to multiply each mass times the Y value. So that's going to be the mass of 4. So that's going to be a mass of 4 times 2 plus a mass of 3 times 3. This needs to be 4 times 2 plus 3 times 3 plus 11 times -4 and 1 times -2. All right, so that's -29. And then we need to find MY. All right, so we need now the masses times the X values. So that's going to be 4 times -2 plus 3 times 1 plus 11 times 7 plus 1 times -3. And that's 69. Okay. All righty. So now we can get this. So now our M sub X, let me erase that for a moment. I can do it this way. So now I have M and no, X bar is what I want. X bar, I want X bar. Okay, so X bar is going to equal, go back. X bar is going to equal Now, how do we do this? Which one goes over it? It's my, right? Which is negative 29, divided by our mass m, which is 19. And that's roughly 1.5. So it's going to be 1.5, okay? And our y bar is going to equal 69. That's a big number. Whoa, not that big. 69 divided by 19. 3.6. Okay. I don't believe that. Mx was 4 times 2 plus 3 times 3 plus 11 times negative 4 plus 1 times negative 2 gave us negative 29. That's because these are backwards. They're backwards. Mx is supposed to be my. Sorry, guys, I did it wrong. 69, I knew right away it was wrong because it didn't look like it didn't fit. Okay, and then this one, y bar is supposed to be mx. I don't know why I got it wrong again because my brain just said 29. And now it makes sense. Okay, now it makes sense to me. Okay, so now my center of mass is to go 3.6, which would be 1, 3.6 here, down 1.5, so roughly right around there. So that is X bar, Y bar, right there, center of mass. I made it blue. Okay. All right, nope, we're not last. We still got 2 more topics. Mass of a lamina. Any questions about what we've done? I know I complicated it once, but I'm sorry. I keep putting the M's in the wrong place. Mx is my over m, and y bar, x bar is my over m, and y bar is mx over m. Okay. So now we want to look at the mass of a plane region. So now we don't have something like this, where we just have point masses. Okay, so these are point masses. Now I want to look at something a little bit different. Okay. Goodbye, E. Okay, so let's just suppose I have a mass now, and this mass is defined who knows what. So here's my mass, and this curve is y is equal to f of x. Okay, and so now this under here is my region. So this is the region I'm looking at, the whole region. And I need to find the center of mass of this region, given it goes from some A to some B, and that's the function. So now you can see I have a region enclosed by the x-axis and the function y is equal to f of x. So I'm going to do the same thing I did before, but this time I'm going to take a region that looks like this. And I'm going to find the average of this region. So the average might be, average XF might be here. So that I'm going to approximate my f of x. So this now is delta xk. And there's some xk in the middle and its function value, actually I should make its function value more like that. Yeah. So now I have this. And I'm looking at this. I have 1 minute. Okay. So my mass M, again, is my mass. And if you remember, we're in 2 dimensions now. So my density is mass per unit area. Okay. So that means when I take and find the mass, which is the sum, K equals 1 to N of my MKs or my delta MKs. This is now going to be, well, how do you find the area? So this mass is now going to be delta times area. So this is the sum, K equal 1 to N of my little piece of mass times my area. Oh my goodness, how do I find that? Well, that's easy. If I take the height of the function, which is f of xk, and multiply by this width, I have the area. So lastly, there's no lastly. I'm going to stop here and finish tomorrow. That's it. That's it for today. Yeah.